Welcome to part 4 of our Oracle Database in Memory workshop. In today's session, we're going to cover how Oracle Database in Memory interacts with the Oracle Optimizer. So what does the optimizer have to do with Oracle Database in Memory? Well, of course, the optimizer is the component of the Oracle database that gets to decide the execution plan that's going to be used for a query. And so it is the optimizer who gets to decide if the in-memory column store will be used or not for a given query. Now, traditionally, the optimizer has made its decision about which execution plan is going to be used using a cost model, where we associate different costs for different operations in that plan. And that cost model has been increased or improved to incorporate the new Oracle database in memory column store and the data that's in it. So what it's going to do now is use the basic table statistics that you've always given it. So for example, the number of rows in a table, the number or types of columns that are in that table, are there indexes, are there partitionings, what about a histogram to indicate a data skew? All of that traditional object level statistics, we're going to use those in conjunction with the system level statistics and a new set of in-memory statistics in order to come up with the best execution plan. What does that mean for you? Well, it means that you're going to still have to be responsible for gathering a good set of optimizer statistics. Oracle will automatically take care of both the system and the in-memory statistics in 12.102. So what does this mean for you? Well, the optimizer is going to come up with the execution plan using a combination of system-generated statistics, so the statistics it automatically gets from the in-memory column store, and I'll explain exactly what they are a little bit later on in the presentation, as well as all of the base statistics that you should be gathering for the optimizer, so table statistics, index statistics, as well as column statistics, for example, histograms, to ensure that the optimizer has the best view of the data that it's going to be accessing so that it can determine the best execution plan. So just to quickly recap, I wanted to give you some guidance on how to ensure that you are gathering the best statistics for the tables and indexes in your schema. First thing you want to do is you want to be using DBMS Stats. You want to use the gather stats procedures in this package rather than the analyze command, since that command has been deprecated since Oracle A/I, and it doesn't even gather the correct statistics needed by the optimizer's cost model today. So when you are using DBMS Stats, we want you to use as many of the default parameter values as possible, especially when it comes to the sample size that you're going to use to gather your statistics. We want you to use the auto sample size as much as possible. That's going to help us enable a lot of new algorithms that were introduced in 11.2 and 12c to ensure that we're going to get the most accurate set of statistics and the best information to the optimizer. We also want you to use the default parameter values for the method opt parameter so that we are going to gather the appropriate histograms on the individual columns so the optimizer can be aware of any data skews that may exist and allow us to get a better cardinality estimate for a particular query, and that will allow us or allow the optimizer to determine whether or not this execution plan can benefit from accessing the data in memory or not. If you haven't trusted histograms before 12c, if you thought it took too long to gather those histograms, or the histograms didn't give the optimizer enough information, Well, all of that has changed in 12c. We've introduced a new set of or type of histograms in 12c that provide the optimizer with a lot more detailed information than they ever did before, and it's also much faster for us to gather these new types of histograms in 12c. So if you haven't used them in the past, I would strongly recommend, now that you're on 12c, that you give histograms another chance. It will help the optimizer to get a much more accurate understanding of the data that is being held in the columns in the column store, and so it can determine whether that's the best execution plan or not. You also might want to include extended statistics in your statistics gathering approach in 12c. Extended statistics make the optimizer aware of different behavior or cross-column relationships within your data set. So say, for example, you've got a query that comes in on the vehicles table, and that query always has where clause predicates on the car manufacturer and the car model. Now, you and I know from the real world that certain manufacturers only make certain models of car. So for example, if we know that the model is an M5, we know BMW is the only manufacturer that makes an M5. So when a query comes in and says select star from the vehicles table where the manufacturer is BMW and the model is M5, we know that those two where clause predicates don't in fact reduce the result set, because the result set would be exactly the same if we had simply just said where the model is an M5, because BMW is the only manufacturer that makes that model. Because of that correlation or relationship between these two columns, the optimizer could underestimate the cardinality for that particular query, and so we're going to use extended statistics to make the optimizer aware of that real-world relationship between those two columns. And by having that information available to the optimizer, it can make a much better cardinality estimate, not just for single table queries against the vehicles table, but also for queries that may join to that table or do some type of aggregation on that table. Even though we've mentioned in previous sessions in this workshop that with Oracle Database and Memory we have the opportunity to get rid of some of the indexes in a mixed workload environment, we want to make sure that we do continue to keep the primary key, foreign key constraints, as well as any not null constraints, in order to actually share that information with the optimizer and allow it to know more information about your data set, so we can start taking advantage of as many optimizations as we can for your queries. First thing the optimizer is going to find out is if any of the tables that it's interested in for this query are populated within the in-memory column store. If the answer is yes, it's also going to get some additional information about those objects. So for example, it's going to find out how many IMCUs or in-memory compression units are allocated from the in-memory column store to this particular object. It's also going to know how many IM blocks or database blocks map to those IMCUs. It's also going to find out how much of the table has actually been populated into the in-memory column store. Remember, not all of the data from a particular object, be it a table or partition or materialized view, needs to be populated into the in-memory column store. So we will tell the optimizer what fraction of the table has actually been populated into the column store. The closer that value is to 0, the less data we believe is in the in-memory column store. The closer that number is to 1, the higher the percentage of rows from that table are in the actual in-memory column store. We also want to know how many actual rows are there. So we will tell the optimizer the number of rows in memory. We also want to let the optimizer know how many entries within the in-memory column store may be stale and how many entries there are in the corresponding transaction journals. So all of that information is being sent to the optimizer. The optimizer is also made aware of whether or not we're running in a rack environment and if the data has been distributed across the rack cluster or duplicated across the cluster so that it is fully aware of the data affinity and to make sure it starts enough parallel server processes across the rack cluster in order to be able to access all of that data in memory. So where will the optimizer use this information within the cost model? We actually see it in multiple places. We see it both in the I/O cost as well as the CPU costing for the optimizer. Now, you might be wondering why on earth would it be involved in the I/O cost? After all of the data is in memory. Well, actually, what we're using it in the I/O cost for, of course, is if we've got any invalid entries. And if for whatever reason we couldn't read the corresponding entries from the journal, we do need to go to disk for those. We also read the extent map to get a full understanding of the objects that are being accessed within the column store. But as you can imagine, the majority of the changes have come to the CPU costing, where we're going to include the amount of CPU we believe it's going to take to transverse through all of the IMCUs for this object. We also want to get information on how many of the IMCs can be pruned out due to the storage indexes. We also need to account for some CPU to decompress the entries in the IMCUs that we do scan that need to be returned to the end user. We're also going to take into consideration how many predicates we can offload or push down as part of the scan of the objects within the in-memory column store. And if you're unfamiliar with that terminology, if you're not used to it from Exadata, I'll explain exactly what I mean by that predicate pushing a little bit later on in the presentation. Now, when we access data in the in-memory column store, remember we're accessing it in columns. And so from that columnar data, we need to stitch the rows back together in order to return them to the end user. And so we must account for the CPU required to do that stitching. Finally, we're also going to need to account for any CPU required to transverse or read the entries in the transaction journal. So how can I tell if the optimizer is actually using any of this information? Well, I thought it'd be a good idea for us to take a look at an example. There you see the query on the right hand side of the slide. Select count star from sales where the quantity is greater than 30 or the quantity sold is less than 10 and the product ID is greater than 5,000. We're going to use this query and step through the corresponding 10053 trace or optimizer trace and show you where both the in-memory statistics and the base table statistics are going to be used together to determine the best execution plan or the cost for the best execution plan for this query. So let's start with just the basic in-memory statistics. Where are they going to show up in the optimizer trace? Well, if you look under the base statistical information and you look at the table stats, if you drill down on just the table stats for our sales table, the table used in this query, you see there that it's got the basic table statistics. So for example, the number of rows in the table, 960. The number of blocks required for this table is 12. The average row length is 30 bytes and so on. What you'll also see is a new set of statistics there. These are coming straight from the in-memory column store. You're going to see the number of IMCUs for this particular object or for the sales table, that's 7. Number of rows is 560. Number of blocks is 7. And you'll see there that the fraction of the table that's actually been populated into the in-memory column store is about 60% or 58% of the table. Now, how do I know that's accurate? Well, if I look at the total number of rows in the table, there are 960 rows in the sales table, but there are only 560 of those rows populated into the in-memory column store. So for whatever reason, either we chose not to populate a particular partition or we ran out of space when we were populating the sales table, not all of it has been populated into memory, which is why that fraction doesn't show 1 for 100% of the rows being in memory. It shows 58% of the rows are actually in memory. The other place where we're going to see the in-memory statistics being used in the in-memory column store, of course, is going to come with the scan costing. So both for the I/O and the CPU costings, we're going to include information from the in-memory column store. And you see it there as part of those scan operations. We've got a new calculation now, which is for IMC, or in-memory column store. We'll see that we'd have to read some invalid rows as well as the extent map from disk. And so we need to factor that into the costing of the scan of the sales table. We'll also see changes to the calculation that's done for the CPU costing for the scan. Now, there's a lot more information here. As I said, we're looking at information, for example, what benefits we get from the min-max pruning from the storage index, how expensive it would be to stitch the rows back together, the number of IMCUs that need to be touched, the number of columns within those IMCUs that need to be touched. Now, I certainly don't expect you to study this formula or algorithm or know it off by heart or anything. I just wanted to show you that how and where the cost model is being influenced by the presence of the in-memory column store. The final place where you'll see all of this information being brought together then, of course, is in the final calculation where we do the total scan IO cost and the total scan CPU cost, using that information, using the statistics together. And that's what's going to influence the decision to either access the object within the in-memory column store or not. And of course, that will influence the access path, because when we access data within the in-memory column store, we're always going to do a full scan, where other alternatives could be an index range scan or a unique index lookup and so on. And so all of those options are going to be costed, and the optimizer will pick the plan with the lowest cost. So earlier on, I mentioned the fact that the optimizer needs to be able to cost the fact that we can push predicates to be executed as part of the in-memory scan. And by that I mean that your where clause predicates from your queries will actually be evaluated during the scan of the data within the in-memory column store rather than afterwards. So what does that mean? Well, for starters, once we know what columns are in the where clause predicate, we know which columns we need to access from the column store, and we're only going to access them. We also know that based on your where clause predicates, we can take advantage of the storage index and dictionary pruning in order to only scan the IMCUs that hold the values that we're interested in for this query. And of course, those where clause predicates are applied to the values within the columns that we are scanning via the SIMD vector processing. That's going to allow us, remember, to do that array processing or set processing on multiple values from the column in a single CPU instruction, allowing us to really execute the query much more efficiently. Now, of course, the standard where clause predicates that you supply in the query are eligible to be pushed as part of the scan, but we also do implied predicates. Implied predicates are actually derived from the where clauses you have in your queries in conjunction with information we've got, for example, primary key, foreign key constraints, not null constraints, and using that information with your where clause predicates and basic logic, the optimizer developers are actually able to apply additional predicates that are true, but you may not have realized when you were writing the query. And we're doing that, of course, based on all of that lovely logic that you probably looked at in university and haven't thought about since. A quick example of some of those types of things on the slide there. Don't worry, there's not going to be a quiz on that. Let me give you an example based on real-world information that can make it a little easier perhaps to understand the whole predicate push scenario. Say, for example, you issue a query that says where column 1 is equal to 2, or column 1 equals 1 and column 2 is greater than 1. Based on that information, the optimizer developers can actually determine an additional predicate that says basically where column 1 is in 1 or 2. So by giving us that in list, it allows the optimizer to push a new predicate on column 1 that says basically don't return any entries from column 1 when you scan it unless it's got a value 1 or 2. And by pushing that implied predicate down into the scan in the in-memory column store, we're able to execute the query much more efficiently because we're not going to be returning all the values from column 1, only the values that are in 1 or 2. Now, these implied predicates that we are pushing down as part of the scan, along with any where clause predicates you actually defined in the query, are visible in the 10053 trace or the optimizer trace. And I'll be able to show you that example now. If we go back to our simple query where we're select count from the sales table, you'll see the implied predicates there at the bottom of the screen in the 10053 output. You see there that we are using. So if we go back to our query against the sales table, where we had predicates that said where the quantity sold is greater than 30 or the quantity sold is less than 10 and the product ID is 5,000, let's take a look at the implied predicates the optimizer came up for that in the 10053 trace. Well, what you see there is that we do have some implied predicates for the sales table, and what we've done is we've rewritten the where clause predicate to be where quantity sold is greater than 30 or quantity sold is less than 10. So by defining a specific predicate or range predicate on the quantity sold column, as we've done here, it means that we'll be able to scan the quantity sold column much more efficiently, only return the values that fall within that range, so values that are greater than 10 but less than 30. Based on that information, then we'll apply the additional where clause predicates to those corresponding entries in the other columns in the column store and get a much more efficient execution plan for our query. So how can I tell what the optimizer is thinking and whether or not it is actually going to pick the in-memory column store or not? Well, the first place we need to look for any information about what the optimizer is thinking is, of course, in the execution plan. So let's say, for example, our sales table that we've been using in all of our examples so far is actually on an Exadata environment, but it's not been marked in memory. If we look at the execution plan for that, we're going to do table access storage full on the sales table, probably the most efficient execution plan given the fact that we're on Exadata, and that scan of the table can be pushed down to the Exadata storage cells, being able to take advantage of Smart Scan. And I see that the predicates being pushed down to that scan inside in the storage are the predicates just as they're defined in the query today. So where quantity sold is greater than 30 or the product ID is equal to 5,000 and the quantity sold is less than 10. So no implied predicates being defined there, simply taking the predicates that were in the query and pushing them down to the storage. That's how it's going to work on an Exadata environment. Now, if the sales table was marked in memory, how would the execution plan differ? Well, first, if we look at the plan itself, you'll see there that the access method has changed. We're now doing table access in memory full. So that's the first change. So we're going to access some or all of the data from the sales table from the in-memory column store. But if we look under the execution plan, what you'll actually see is that there are additional predicates being passed to the scan in the in-memory column store versus on the Exadata storage. And these are the implied predicates. So if we take a look underneath the execution plan at the predicate information, we see an additional where clause predicate or implied predicate has been created. That's the range predicate that we looked at earlier on. So where quantity sold is less than 30 or quantity sold is greater than 10. And of course, the actual predicates that showed up in the where clause of our particular query. So we're going to offload both of those, allowing us to get a much more efficient scan of the quantity sold column as well as the product ID columns when we're accessing the data within the in-memory column store. Now, what's interesting to note is that even though we are using additional implied predicates and the access method has changed from table access storage full to table access in memory full, the plan hash value for this query has not in fact changed. Now the reason for that is that the special area where we're storing the keywords storage and in memory are not in fact used to calculate the plan hash value. So by changing that keyword from storage to in memory doesn't actually change the plan hash value. It's simply ignored that keyword. But what if not all of the data fits in memory and I'm on Exadata? Will I see in memory in the execution plan in that keyword, or will I see storage? Well, if we look at the execution plan for our query, where some of the sales table has been populated in memory, but the rest of it is out on disk on an Exadata environment, what we'll actually see is that the execution plan will show the keyword in memory rather than in memory/storage or whatever you thought it might show. Now, the reason it only shows one of the keywords and it only shows in memory is that there's only room for one keyword in the plan table. We don't have room for longer words than that, and so we couldn't put in memory/storage. The other reason is that the in-memory will get preference. We'll access as much of the data as we can from the in-memory column store and only go out to disk for the data that we can't find within the in-memory column store. The advantage of running a query where not all of the data will fit in memory on Exadata is that the implied predicates that are calculated or generated by the optimizer for the in-memory column store can also be offloaded to the Exadata storage. So we'll get some added benefit from those scans on Exadata than we would on any other platform. And again, the plan hash value has not changed. It remains the same because that keyword, remember, is not being used to calculate the plan hash value. That means if you're migrating a workload or a data set from an existing non-Exadata environment into Exadata, you're not going to have any issues with plan changes because all of the plan hash values should remain the same. Let's look at some of the optimizations or transformations that have been put in place to help the optimizer determine the best execution plan for Oracle database in memory. And not all of the data I want to access can reside in memory. Well, let's take a look at an example. I have a sales table. It's made up of two partitions, one for open orders, which is very critical to the business. So I've placed that partition, P1, in memory. The second partition is for our closed orders, and that's a much larger partition, too large, in fact, to be populated in memory. And so order status equals closed, that information is all out on disk. Now, in order to make sure that I can access that data efficiently, I have created an index on the order date, which is typically used in the where clause predicate of my query. So typically I get the order status, which allows me to do partition pruning, and I get the order date, which will allow me to get a faster access to those closed orders that are out on disk by taking advantage of that index. So when I'm accessing open orders, full table scan in memory. When I'm accessing closed orders out on disk, it's typically via the index. But what happens when a query comes in that has the following? Select star from the sales table where the order date is between the 1st of January 2013 and the 31st of December 2013. So I want to look at 1 year's worth of data that may encompass some open and some closed orders. So if I'm doing that, what execution plan would I pick? If it's only open orders, then the best execution plan would be table access in memory full, just as we saw before. But if I'm accessing the closed orders, the best execution plan would be an index access. So which approach is the optimizer going to choose? Does it choose full table scan so that it'll be fast for the open orders but much slower for the closed orders because I can't use smart scan because I'm on commodity hardware? Or do we go with the index access and bypass the in-memory column store completely? Well, actually, the optimizer is going to take the best path for each piece of the data by rewriting the query using an optimization called table expansion. What we're going to do is rewrite the query as a union all with one branch of the union all statement going against the partition in memory, the other branch going against the partition on disk. By creating separate branches in the union all statement, it allows us to access the data in the most efficient way for each set of data. So via table access in memory full for the partition P1 that's in memory, and via the index range scan for partition P2 that's out on disk. One of the other areas where transformations come into effect with the in-memory column store, of course, comes in the form of joins, and the fact that we're able to speed up the joins that are used in the in-memory column store by being able to take advantage of something called a Bloom filter. Now, a Bloom filter, remember, is going to convert a join into a scan and filter operation that will perform incredibly efficiently inside the in-memory column store. Now, the Bloom filter technology is not something that's new. Remember, it came in Oracle Database 10G, and it is the same technology we're using to offload joins to the Exadata storage today. But what happens if I've got a query with multiple joins? Am I still going to be able to generate a Bloom filter for that? Well, yes, it is possible for the optimizer to generate multiple Bloom filters and use them together on a single table scan by taking advantage of an optimizer transformation called swap join inputs. And I'm going to explain exactly how that works right now. So here we've got an example. I've got a 4-table join between line orders, date dimension, part, and suppliers. And I want to make sure that I'm going to execute the scan of the line orders table, which is the big table in this query, as efficiently as possible using as many Bloom filters as possible. As you can see, we did get multiple Bloom filters created. That's the good news. And all of those Bloom filters are being used as part of the scan of the line orders table. But exactly how is that going to work, given the fact that those smaller dimension tables all only join to the line orders table? Well, instead of creating the traditional left deep tree, as you see here, what Oracle actually did was apply swap join input transformation that allows that left deep tree to be turned into a right deep tree. And actually, instead of starting in the lower left-hand corner, where we actually start the execution now is in the upper left-hand corner, and we would start by scanning the date dimension first, apply any of its where clause predicates. Based on that scan, we'll get a result set that we hold in memory, and we'll also get a Bloom filter that we can use as part of the scan of the line order table. Now, rather than moving on and doing the line order table next, we'll actually move on and do the supplier table next. Again, we'll apply any where clause predicates we have to supplier. As part of that scan, we'll generate a Bloom filter that can be used as part of the scan of the line orders table, and that result set and Bloom filter will be held in memory as we move on and scan the parts table next. Again, apply any where clause predicates we have to the part table, generate a Bloom filter as part of that scan, and all 3 Bloom filters can then be used as part of the scan of the line orders table. Then and only then, after we've scanned the line orders table, extracting only the values that we need that satisfy our Bloom filters, will we do the join backs via hash join to those dimension tables. By being able to apply those multiple Bloom filters as part of the line order table, we can greatly reduce the number of rows that are going to be sent back up the execution plan via the hash joins and any group bys and so on that we need to do in the rest of the query by applying those Bloom filters as part of that scan. The final transformation we're going to look at is in-memory aggregation. So let's look at a quick example so that we can refresh our memories on what in-memory aggregation actually is all about, and then I'll explain how this optimization works in detail. So we're going to look at a sample query here. It's a 3-table join between sales, customer, and the time dimension. And what we're actually doing is reporting the total amount of sales we had for our different regions by quarter for a given year. And so what you'll see there is our join conditions between the different tables, as well as our where clause predicate on the year that we're after. Now, we're going to execute this query using in-memory aggregation. Remember, that's allowing us to take advantage of an in-memory accumulator or report outline that's going to allow us to do the group by as part of the scan of the main table, in this case, the sales table in the query. So let's step through the execution of this query. So the first thing we're going to do is we're going to start by scanning the 2 smaller dimension tables. We're only going to access the columns we need for the query. So we'll apply any where clause predicates we've got, and we'll extract out the information that we need. So remember, we're trying to aggregate the data by region and by quarter. Based on the information that we get from those dimensions, we're going to do 2 things. First, we're going to create these key vectors, very similar to a Bloom filter, that are going to allow us to execute the join as part of the scan of the sales table, but we're also going to create a multi-dimensional array or accumulator in memory Now, because I've only got 2 dimensions, it's a 2-dimensional array, and so it's much easier for me to imagine that array similar to a spreadsheet in memory. Now, using the key vectors and the spreadsheet, we're going to do both the join and the aggregation as part of the scan of the sales table. So let's look at the first entry in the sales table. It's got a date ID of 5, customer ID of 2, so a customer region ID of 2. What we'll do is we'll look at the corresponding entries in the key vector. So for customer 2, that'll be the second location in the customer key vector, so that'll have a value 3 on the spreadsheet. And for the date dimension, I'm going to look in the 5th entry of that, and it's going to give me the value 1. So I'm going to put the total sales for this particular entry in the sales table, which is 10, into the cell that is 3-1 on the spreadsheet. So let's try that again. If I move down to the next entry in the sales table, date quarter has an ID of 4, the customer region has an ID of 6. So I go to the 6th location in the customer key vector, that's got the value 4. I go to the 4th location in the date dimension, that's got the value 2. And I'm going to put the total sales for this entry in the sales table into the cell 4-2 on the spreadsheet, which is why the value 20 appears there. I'm going to move on to the 3rd entry in the sales table. It's got a date value of 1 and a customer value of 7. Date value of 1 gives us a 0. Customer value of 7 gives us a 3. And what we'll find is there is no 0 for the date listed on the spreadsheet. The first date we've got is a value 1. That means that that particular quarter that's being returned by the sales table is not in fact a quarter in the given year that we're interested in. A value 0 in the key vector basically means no match. That is not a quarter that we're interested in. It doesn't match our join condition, so we skip that entry in the sales table and we move on to the next one. And you'll notice nothing got added to our spreadsheet or our multidimensional array in memory. That's our accumulator. If we move on to the next entry, that gives us a value 2 in the date dimension and a value 7 in the customer dimension. So if we find those in the key vectors, that gives us a value 1 on the key vector and a value 3 on the customer vector. And we already had the value 10. If I go back, you'll see we already had the value 10 in that cell in the spreadsheet. Now we need to add the new value to the existing value. So we add the value 5 to 10 and we replace the value in that cell in the spreadsheet with 15, so that by the time I finish scanning the sales table, I have the total amount of sales for our different regions by quarter for this given year. I simply need to return that spreadsheet to answer the user's question. How does it look in the execution plan? Well, you can see all of those detailed steps we've just gone through actually in the execution plan. First part, remember, is scanning of the dimension tables. You see that there on line 6 and line 10 of the execution plan. The next thing we need to do after we scan those dimension tables, remember, is to create the key vectors. So you see that creation being done there on line 9 and line 4 of the execution plan, one for each of the dimensions. The next thing you see is that we're going to create these temporary tables. Now, those temporary tables are created to hold what we call the payload columns. Now, this is technically a step. I didn't show you my little diagram on the previous slide. This step, as I said, is going to help improve the efficiency of the query by parking basically the payload columns somewhere and only picking them up again at the very end of the execution. Now, the payload columns are the other columns that have been selected on the select list from the dimension tables, but they're not needed to facilitate the join and the aggregation. So for example, that's information like the region name and the quarter name and so on. And so we build these temporary tables using these payload columns, and we define something called a dense grouping key, or we give those entries a unique key that's going to allow us to be able to join the accumulator back to these payload columns that are stored in these temporary tables right at the end of the query so that we can return the final result to the end user. Next, we're going to need to scan the sales table or the fact table, applying all of our key vectors to complete the join as part of the scan, and then filling in that multidimensional array or the spreadsheet in memory so that we can do the aggregation as part of that scan. And you see that all going on there on line 21 is the scan of the sales table. You see line 18 and 19, the key vectors are being applied. Line 16 of the execution plan is the actual completion of the accumulator or the vector group by. Then the very last thing we're going to do at the end of the execution plan is join the results of our scan of the sales table to those payload columns that we've stored in the temporary tables, and we do that using the hash joins there and the hash group by. That's going to allow us to complete the query and return the final results set to the end user. So as you can see, vector group by is, although a complex transformation to understand, it is going to really improve the performance of your queries. But I should warn you, it's not going to kick in for every group by query that you've got, just because the underlying table is in memory. So one of the first things I'm going to bring your attention to is the fact that if you've only got a single table in the query in this initial release 12.102, then it is not eligible for vector transformation. That won't happen until 12.2. But if you do have multiple tables in the join, then vector group by is eligible. We need at least one or more small tables to be joined to a much larger table in order to get vector group by. Typically, we want the smaller table to be about 1/10 the size of the larger table in order to trigger vector group by to be chosen by the optimizer. We also need equality joins between these dimensions in the fact tables. Of course, the query needs to have some type of measure in it that's going to trigger aggregation. So for example, maybe it's a count distinct, a sum, a max, a min, something along those lines needs to be in the query in order to get it to generate it. And of course, your query needs to contain a group by clause. Now, the final section I want to cover today is controlling all of these changes. As you can imagine, the fact that the optimizer is going to be changing execution plans based on the information that it's got about what tables are in memory and how much of those tables are in memory, you're bound to want to be able to control it to a certain degree. So let's look at the different init.or parameters you have at your disposal. There's one new optimizer parameter to do with in-memory. It's called optimizer in-memory aware. It's a Boolean parameter, so it's either true or false. By default, it's true, and that means that the optimizer will use the in-memory statistics and information and adjust the cost model to accommodate those new statistics each time it's coming up with an execution plan in your environment. Now, if you set it to false, on the other hand, then what you're telling us is that don't factor in any of the information you know about the in-memory column store when you're coming up with the execution plan for my queries. Now, that doesn't mean that the query still won't actually benefit from scanning the data in memory if the execution plan we come up with does use a full table scan or a full partition scan, but the costing of the query and the execution plan won't factor in any of the information we have about the in-memory column store. Alternatively, you can also disable the costing of the in-memory column store by setting optimizer features enabled to less than 12.102. Any value less than 12.102 will disable all of the in-memory enhancements to the cost model, but also all of the enhancements made in 12c in general to the cost model. So be careful with that. You're going to disable a lot more than just the in-memory stuff. And again, it won't prevent the query from executing in the in-memory column store, but it will prevent us from costing or taking advantage of the costing for the in-memory column store. But if the query determines that it's going to be a full scan of some kind, then we may indeed use the column store. If, on the other hand, you don't want us to cost or scan the data via the in-memory column store, so you don't want us to basically execute the query as if the in-memory column store no longer existed, for that, you want to use the new in-memory parameter called in-memory query. Again, it's a Boolean parameter, either true or false, and it's set to true by default, but if you want to disable all knowledge, all access to the in-memory column store, set in-memory query to disable, the plan will be costed based purely on the disk statistics, and we will scan from disk. We will not scan from the in-memory column store. So if you are trying to do testing, how much benefit am I getting from in-memory? I would suggest that you use in-memory query rather than using optimizer in-memory aware or optimizer features enabled. All of those parameters are session settable, so you can do any testing you want, but if you are going to do that type of testing, I would recommend in-memory query versus the other two optimizer parameters. If you want to actually hint that a particular query or a particular table within a query should be accessed via the in-memory column store, then you can do so using the in-memory hint. Now, if you simply specify in-memory, then what you're looking for is to force all of the tables that are in the query to be scanned via the in-memory column store. If you use in-memory open parentheses and you specify a given table name, then it's simply just that particular table is not going to be or will be accessed in memory. If you do no underscore in memory, again, open parentheses, specify a table, then it's just that table within the query that won't be accessed from the in-memory column store. Now be very, very careful. The in-memory hint does not trigger a table that has not been marked in memory to be populated into the in-memory column store. In-memory is simply a hint that allows you to direct the optimizer whether to scan an existing object in the in-memory column store or not. The other place that you might want to influence is whether or not we use the new vector group by or the new vector transformation. And again, you can do that using a hint. The hint is called vector transform. That's going to force the vector group by on a particular query block. And that is, of course, if the transformation is possible. If you don't want us to use vector group by, if you want to prevent the transformation, then you want to specify the no vector transform hint. So where can you get more information about Oracle Database in Memory? Well, there's a wealth of information available at your fingertips, either via the in-memory blog or the oracle.com website. You'll find white papers, videos, demos, as well as other webcasts that you can replay and listen to about Oracle Database in Memory. And of course, if you've got any questions, you can always reach out to me, Maria Colgan at oracle.com, or submit a question to the Oracle blog, and we'll do our best to answer any of those questions for you.